Richard Feynman once famously compared the study of science to the study of chess. You observe the game. You learn how the pieces move. You think you understand the game pretty well. Then something strange happens in the corner, and it's castling. Richard Feynman also once said, if you thought that science was certain, well, that was just an error on your part. With that thought in mind, we'd like to have a discussion about the principle of conservation of momentum. I should confess to a decidedly unscientific agenda on this subject. We have a pronounced interest in not just the exploration, but the conquest of space, and the principle of conservation of momentum is limiting our aspirations in that arena. So, the principle itself, to every action there is always opposed an equal reaction, or the mutual actions of two bodies upon each other are always equal, and directed to contrary parts. We should note here that that's not a proof. That is a statement, an axiom, a distillation of our ubiquitous experience to a simple rule that we generally accept as a universal principle. That statement can be couched in many different and useful forms. None of these constitutes proof. Each of these is a restatement of the original axiom. We'd also like to note that Newton formulated the principle of conservation of momentum in the context of interacting bodies. The mutual actions of two bodies upon each other are always equal and directed to contrary parts. What if we only had one body? What if we could induce a force on a single body without involving a second body? I think, by definition, momentum would not be conserved in that case. But let's leave that aside for a second and get a little more rigorous. Let's talk about Emmy Noether's first theorem. Noether's first theorem shows that for physical systems with conservative forces, certain symmetry properties correspond with certain conservation laws. In particular, the uniformity of space corresponds with the conservation of momentum. The uniformity of time corresponds with the conservation of energy. Now, how cool is that? Ms. Noether showed us not only that conservation of momentum is required, but when it is required and why it is required. In particular, it is an analytical consequence of certain symmetry properties of space itself. Let's look at that a little more closely. We mentioned conservative forces. One aspect of a conservative force is path independence. That is, the work done in moving an object from point A to point B is the same irrespective of the path taken, whether to the right or to the left or some circuitous path in between. This also applies when other bodies are involved. If two bodies interact, shown schematically via an electric field here, then any work gained by one particle must be at the expense of the other. Okay, but what if space is not uniform? What if we have a region of space that, for example, contains a stable electric field, not associated with any second mass? When the particle moves through that region, it gets a boost, and that boost is derived solely from the electric field in that region of space. So, if we have a free space electric field, and that field does work upon a charged particle, in that system, without translational symmetry, linear momentum need not be conserved. In fact, it can't be conserved because there is no second mass to receive the opposing momentum. In the language of Noether's theorem, delta S is not zero. Now the good news, that's what a laser is. A free space laser beam is a little more than an oscillating electric field. That electric field is not associated with any mass. We'll get back to that in a second, and can operate on a charged particle precisely in such a manner that the particle no longer has translational symmetry. We can cite two examples of this phenomenon. First, an electron moving under the influence of a laser beam. The electrons begin to move horizontally in the beam propagation direction as a result of photon pressure, the momentum of the incident photons we mentioned a minute ago. It also begins to move perpendicular to the beam propagation direction, the transverse direction. The movement perpendicular to the beam is solely a result of the electric field of the laser beam upon the charged mass of the electron. One may argue that there is a process by which the electromagnetic field momentum is converted to linear mechanical momentum, and that total momentum is conserved in that process. Even if true, we would argue that if we can generate electromagnetic field momentum at will with a laser, and then convert that to linear mechanical momentum, that is sufficient to achieve the condition wherein the principle of conservation of momentum is no longer a constraint. We can cite a second example of a force induced solely from an electromagnetic field, in the case of optical trapping. In this case, again, there is a force upon the sample parallel to the beam propagation direction as a result of photon scatter. But there is also a force perpendicular to the laser direction due solely to the electric field of the laser acting upon the induced dipole of the sample, the gradient force. This looks very promising. If we can induce a force on a target solely from a free space electric field not associated with a second mass, that could be useful. Of course, the laser is not static in space. It travels in a wave and oscillates quite quickly, so any static charge, like an electron, will not see much force over time. But we can manifest a net force when we change the effective charge on the target in sync with the laser field oscillation. Whether by the same process as that in optical trapping or other, we can set the charge to be positive for a positive laser antinode and set the charge to be negative for a negative antinode, and repeat the process. In such a case, the sample will get a little nudge in the transverse direction at each passing antinode of the laser. Okay, now the really good news. We can transfer the force on the target to any device or enclosure we choose. In particular, since the laser is a free space electric field, not associated with any mass, not even the mass that emitted the light in the first place, our enclosure can include the laser emitter on the same platform that manifests the transverse forces. Yes, that looks very much like a propulsion system that is not constrained by the principle of conservation of momentum, since in manifesting a free space electric field and utilizing that to produce a force on a target, we have, in effect, broken the translational symmetry of the system. We conclude with another quote from our esteemed Mr. Feynman, and with noting that science, while being infinite in its promise, can never be infinite in its certainty.